Okay, so last time we studied how inverse Compton works. In particular, we saw that the average gain, the most important, one of the most important things to remember is the average gain, which scales with gamma squared, with gamma, where gamma is the Lorentz factor of the electron. In particular, we just focused, the very last thing we did, we focused on two boundary case, I would say. So the maximum energy gain, which is a factor of 4 gamma squared, and this is just the boosting.
Scusi, mi sa che non ha condiviso lo schermo.
Okay, sorry. Yes, you're right. Can you see that now?
Sì, sì, grazie.
Okay. Okay, sorry about that. I felt that I was missing something, so that's what I. Okay, so I was saying we just focused on these two examples. So the extreme gain, 4 gamma squared times the original energy of the photon before being upscattered by the electron, and then also the other extreme case in which you have a decrease of the energy. But most of them we will see. Today we will obtain the average gain. So for a given population of photons. So let's review a few examples, practical example, where in astrophysical example, of course, where the inverse Compton can be relevant. So I remind you that the condition that must be fulfilled in order to we have a gain of a factor of gamma square in the energy by the photon, is that in the comoving frame of the electron, the energy of the photon in that frame has to be negligible with respect to the rest energy of the electron, which means in the comoving frame of the electron, the scattering has to be Thomson scattering. And given that you can express this condition in the observer frame, in the lab frame, if you remember that just the energy of the photon in the comoving frame is just gamma times Lorentz transformation, the energy in the lab frame. So the condition that must be satisfied in order to make sure that the Thomson scattering is indeed the case in the comoving frame is gamma epsilon. Epsilon, I remind you, is the energy of the photon before scattering in the lab frame, has to be negligible with respect to the rest energy of the electron. As an order of magnitude estimate, you know that the rest energy of the electron is 511 keV. So let's be conservative. Let's take the order of magnitude as 100 keV, which means that the final energy of the photon, again in the lab frame, which is gamma squared time epsilon max, has to be what? Well, gamma times the maximum energy, gamma 100 keV, because you get back in the lab frame. So it's gamma times this energy. So it means that as soon as the energy of the electron, the energy of the photon, is such that gamma epsilon is not greater than 100 keV, and as a consequence, the resulting energy of the photon will be gamma times 100 keV in the lab frame. You see that when gamma can be orders of magnitude. So it means that in the end, you can end up with an inverse Compton with the final energies of the photon, which can be extremely large because you have 100, so 0.1 MeV times gamma. So the final energy of the photon can be really, really high. Let's see a few examples. Of course, the important is to remember that when you move to excessively too high energies, then you also have to consider that in the comoving frame of the electron, you have the Klein-Mishina limit. When you move in the comoving frame of the electron, of course, when the Thomson scatter is no more valid, you also have the suppression of the cross section. I already mentioned that in many astrophysical contexts, you might end up with electrons having Lorentz factor of 10 to 100, 1000, and even more. We will see. We already mentioned that in the case of the Crab Nebula, that we will comment again. But let's review a few examples. So let's consider, for example, electrons with ultra-relativistic. We are talking all the time here of ultra-relativistic electrons, okay? Given that we are talking about inverse Compton, so it's the electron which gives energy to the photon. So let's consider Lorentz factor of the order of 1000. That means that the gain factor, gamma square, is of the order of 1 million. So for example, if you consider radio photons, so with a frequency of the order of 10 to 9, so the gigahertz, and these photons are upscattered by the electron. So it means that, again, 10 to 6 gain, so it means 10 to 15. You start with a photon, with a radio photon, and you end up with a UV photon, 10 to 15 Hertz. It means that you are in the range of the UV range. So really effective way to turn low energy photons into high energy photons. Another example, these are real examples in which we indeed see this happen. Another example, if you start with far infrared photons, whose frequency is in the range 3, 10 to 12 Hertz, typically emitted in some kind of galaxies, which are characterized by a powerful infrared emission. You see that when these photons cross regions filled up with ultra-relativistic electrons like these ones, you end up that some of these photons are upscattered and become X-rays. So 10 to 18. I remind you that soft X-rays, you are in the range 10 to 17. 1 keV is 2.4 10 to 17, just to remember. So this is just one order of magnitude higher, 3.3 times 10 to 18. So it means instead of 1 keV, 10 keV. So 10 keV, so this is X-ray. And also, if you start with little more energetic photons, like for example optical photons. Optical means something times 10 to 14 Hertz. You see that multiplied by 10 to 6 means 10 to 20, something times 10 to 20. So this is gamma rays, MEV. So just looking at the way you can turn relatively low energetic photons into extremely high, extremely energetic photons. So this is a very powerful way which we see in place in many different contexts. I will just make a few examples, but there are many examples that can be done also depending on the context. What I would like now to do is somehow lengthy calculations about the power emitted through inverse Compton by an electron, which is traveling, by an ultra-relativistic electron, of course, which is traveling within an isotropic population of photons. So where the only assumption that I make is that this population of photons is just isotropically distributed, okay? With some given energy spectrum. So I can consider that photons of any energy. I don't care about that. The only assumption is that in the lab frame, so the frame in which the electron is moving ultra-relativistically, this is traveling within a region filled up with an isotropic population of photons. So you immediately see that what happens is that the electron will scatter some photons, so will give energy to some photons. So some of these photons will be upscattered and will gain energy by a factor of gamma square. Now, because of conservation of energy, of course, this means that the electron cools down, because not just after one single photon, but when per unit time, you have to imagine that it keeps just giving energy to photons. So the goal that the task that we set to ourselves is now to find the power emitted by or lost by the electron and given to the photons. So power, so the amount of energy lost per unit time because of inverse Compton scattering. The proof that we are going to see is neither the smartest nor the shortest. Is the one I myself conceived. I find it somehow intuitive. Well, that's because that's my proof. But this is also an opportunity to provide you with an alternative proof. Then I will advise you also which other proofs you can find in the literature, in particular in the textbooks that I advise. So let's see the key point. So the problem we start with is in the lab frame, where we have our electrons moving relativistically, and here the field of photons is isotropic. The goal is to move and to carry out calculations in the comoving frame of the electrons, and then getting back to the lab frame. This is really convenient. Why? Because if you think of the inverse Compton as we saw it so far, in the comoving frame, it's just a matter of Thomson scattering. So if you think of what happens in the comoving frame, you don't have a redistribution of energies, because from the point of view of the electron just changes direction to each photon that scatters. So the role of the electron in the comoving frame of the electron itself is just to scatter photons without changing their energy in the comoving frame. This brought it back to the lab frame, means a net energy transfer. This is quite interesting. So let's see the idea. The key idea is that if we call E gamma, or better, the time derivative of E gamma, this is the net energy lost by the electron per unit time. So in the lab frame, how the energy of the electron changes as a function of time. We can see it as the sum of two contributions. What dE out is the total energy of the photons that have been upscattered per unit time. The total energy of the photon. But of course, you have to consider that that's not all the energy lost by the electron, because you have to remove the initial energy of the photon. Of course, the initial energy of the photon is something that they already had before the scattering. But you want here to calculate just the energy lost by the electron. So we calculate all the energy of the upscattered photon minus their initial energy. And all this per unit time, of course. So this is the idea. So we will calculate both quantities on the right-hand side of this equation separately, okay? So let's begin with the first one. Well, this is something that we already used once at least, which is the fact that when you measure the rate of change of the energy of, in this case of one particle of the electron, you can, this ratio, so energy, so E out is the, if you think, is the energy of the electron. So is the time-like component of a 4 vector, which is the momentum energy 4 vector of the electron. But you know that this guy here transforms, Lorentz transforms exactly in the same way as time. So it means that their ratio is the same, where prime means calculating in the electron's comoving frame. So this ratio can be easily calculated, can equivalently calculated in the comoving frame of the electron. So now let's set this. Well, you can think of all the energy resulting in the comoving frame. In the comoving frame, the amount of energy that comes to the electron is the same that gets out. because the electron in the comoving frame doesn't change the energy of the photon. So we can calculate just the incoming energy, the energy carried on by the photons against, let me say, the electron in the comoving frame. But this means that you are integrating the specific intensity, and mind, we have to consider all the quantities in the comoving frame, because that's the frame in which we are carrying out this calculation. So I prime, nu prime, the specific intensity in the comoving frame, integrated over the solid angle, times what? Times the area. But what's the area that describes the Thomson scattering in the comoving frame? Well, the Thomson scattering is described by the total cross-section, which is just sigma t, Thomson cross-section. So intensity, specific intensity, times integrated over the solid angle, d omega prime, times the area. You integrate in frequency, so you are left with energy per unit time. And that's all what we need. I'm just weighting all the energy that is being upscattered, that is not upscattered, that is being scattered through Thomson scattering by the electron in its comoving frame. You see? Now, I remind you that you don't know this guy, I prime, in the comoving frame, because in the comoving frame, the distribution is no more isotropic, in principle. So the idea now is to move to the lap frame in the calculation of this guy. To do that, we have to remember how each of these terms transform. And if you remember, that's what we've seen during one of the first classes about special relativity. So for example, I remind you that when you move from the comoving frame to the lap frame, the solid angle element just changes this way. So when you move from here to here, that's what we've seen at the time. This guy here, the solid angle, shrinks by a factor of 1 over delta squared, where delta is the Doppler factor. But here we need to use the inverse transformation. So we need to go from the prime system to the unprime system. So just this way. What about frequency? Well, you remember that when you move from the comoving to the lap frame, you gain an extra factor of delta. Again, you have to consider the inverse transformation. So nu prime is nu over delta. What else? Well, I. You remember very well that I changes with a factor of delta cube. So again, here we have to go from the prime quantity to the unprime quantity. So now we take advantage of what we've seen about that. So replacing, here I remind you what the definition of Doppler factor. Where theta, look, theta is the angle here. So the angle between the incoming direction of the photon in the lap frame and the direction of the moving the moving source direction. So just it's a matter of replacing all the corresponding quantities. So here d nu, so d nu over delta, d omega prime becomes delta squared d omega, and I prime becomes I over delta cube. Here sigma Thomson is a constant, so I just brought it out of the integral. You see that gamma, if you look just at the delta factors, you are left with a factor of delta squared at the denominator. Here we are. Now, since you see this integral is in the lap frame, so you know exactly what is I. I is the isotropic distribution, indeed is isotropic. But if you remember, we derived at the time a relation between the energy density, the specific energy density, and the specific intensity in the case of an isotropic field. If you remember, there was a factor of c over 4 pi. And that's what we are going to exploit right now. So I knew, since I knew is isotropic, so c over 4 pi times what? Well, this guy here, n nu, h nu, is the energy density, or well, the specific energy density. Means energy associated with the photons per unit volume, per unit frequency, where n nu is the specific photon density. So number of photons per unit volume, so over a centimeter cube, it is specific, so it's also defined per unit frequency. So that's why Hertz. But if you know the number of photons within a given frequency interval and you multiply by h nu, that means that you have the energy density, a specific energy density, because everything is per unit frequency. So n nu is the specific number density of photons, so how many photons you have per unit volume, per unit frequency, times the energy of those photons in that frequency interval means that all this guy here is the specific energy density associated with the photon field. So how much energy I have per unit frequency. Okay. So here I just copied the very last equations that we've come up with. So here is the formula for the total power just coming out of the scattering of the electron in the lab frame. And here is I. So by replacing I into this integral, you see that, okay, you get a factor of c over 4 pi. You can get it out of the integral. And also you have 1 over delta squared, but delta is 1 over. So 1 over means that this factor is gamma squared, and here it is. And then you have this term, 1 minus beta cos theta squared, and here it is. Of course, this guy depends on the angle, so I cannot just take it out of the integral on the solid angle, as well as this term here, n nu, h nu, these depend on frequency, so I cannot just take them out of the frequency integral, okay? Just like that. Now, well, we can give some names. So if you integrate the specific energy density, you integrate along frequency, the adjective specific just drops. So it means energy density. And so we call capital U photons. So the energy density associated with the photon field. So how much energy in terms of photon is per unit volume. And this guy here, well, this is just something for kids. If you calculate this guy here, you see there's just a polar dependence on the polar angle. So you have 2 pi, and then if you integrate, you see that the mixed product cos theta just vanishes. You have just 2 terms. I invite you to make sure that this integral is indeed 4 pi times 1 plus beta squared over 3. Make sure you can get it. Small exercise. And so you see there's a factor of 4 pi which cancel out here and here. So you're left with sigma Thomson, speed of light, gamma squared, energy density, and times this factor here. Just like that. And this is just half of the effort that we are supposed to do. Now we have to calculate the second term. All the energy that the photons already have before scattering, which is something that we have then to remove. What we call the E in. So the energy of the photons that before scattering. What is this? Well, this is the total number of photons that are going to scatter the electron per unit time, times what? Well, times the average energy of this photon, okay? So on average, each photon will carry average value of h nu times the number of photons per unit time. And this is the total energy just carried on by the per unit time by the photons that are about to scatter off the electron. Let's work out what average photon energy is. Well, you know the number density. Number density is n nu. So if you consider n nu times d nu is the number of photons having frequency between nu and nu plus d nu, times their energy, h nu, this integrated over the entire spectrum over what? Over the total number of photons. So if you look at this formula here, you immediately see that given that nu is the number density, the specific number density, this is the average, all this ratio is the average value of what? Of this guy here, of the factor that you are weighting with, the number density. So is the average value of h nu. So I just wrote it explicitly what the average energy of the photon is, okay? But let's consider now the dn over dt. Well, if you consider dn, it's just a number. You are counting photons. So it means that if you carry out the same operation, the same calculation in the comoving frame, dn is also dn prime, just the same, exactly the same. So dn here is also dn prime. But what about dt? Well, dt is you have to Lorentz transform. So the same time interval measured in a different reference frame, what we call dt prime, you see that, well, this guy here, dt prime, is a proper time because it's the time interval measured in the comoving frame of the electron. So the relation between a time interval in the lap frame and the dt prime, the proper time interval, you see that you gain a factor of gamma. So the proper time is always dilated by a factor of gamma. So dt is gamma dt prime. Lorentz transformation, proper time. This is convenient. Why? Because now what we are left with is dn prime over dt prime. So the number of photons that are scattering in the per unit time in the comoving frame of the electron. Okay, so this is just I just replaced here the numerator of this factor of what I already defined here. You see, I defined as capital U photons as the energy density associated with the photon field. So as this guy here. So I just wrote explicitly. I exploited the definition. Now let's focus on dn prime on dt prime. Well, we already calculated before integrating, we calculated the amount of energy in the comoving frame of the electron per unit frequency, per unit solid angle, that is scattered by the electron. Now, if you take the very same quantity and you divide by what? By the photon, by the energy of those photons, it means that instead of having energy per unit time, per unit solid angle, you have number of photons per unit solid angle, per unit time, per unit frequency. So I just took the very same quantity that I had before, and I divided by h nu prime. Before I had amount of energy that is going to be scattered in the comoving frame of the electron per unit solid angle, per unit frequency. I take the very same quantity, I divide by the photon's energy. Of course, in the comoving frame, because that's where I'm considering. These quantities are already in the lab frame, but that's because we calculated, then we found this. But what we are thinking of is this quantity is just amount of energy that is being scattered by the electron in its comoving frame per unit time, per unit solid angle, per unit blah, blah, blah. The same quantity divided by the photon's energy is the number of photons that is going to be scattered per unit frequency, per unit blah, 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 which is exactly what we want. And then we have to integrate. Of course, this has to be done before integration, this division, because each single contribution depends on the photon's energy. So that's why we have to do that. But again, nu prime is nu over delta. So you see that in the end, delta square at the denominator, we gain an extra factor of delta numerator. So all this guy here is just 1 over delta. But 1 over delta is essentially the same quantity that we end up here, except that we didn't have, we no more have h nu, because we had h nu at the denominator, and instead of 1 over delta square, as in the previous case, we have 1 over delta. So we have, instead of gamma square, we have gamma, and instead of 1 minus beta cos theta square, we have just 1 minus beta cos theta. The rest is just the same. So if you work out the integral, well, this guy is even more straightforward, because cos theta, just the average value over the solid angle is just 0. So of course the integral of d omega is just 4 pi. So this is even more, this can be easily done just by eye, by visual inspection. You don't need even to calculate this. So again, 4 pi just cancels away. So in the end, you're left with, let's have a look, sigma Thomson, C, gamma, and then this integral. So the integral of n nu, d nu. Now, let's replace dn prime, dt prime into this, which is what we care of. Remind you, we are in the calculation of den, and that's where this factor came in. So den over dt is, I should have 1 over gamma, but here I have gamma, so no more gamma factors. And then I have sigma t c. Here I have u photons. And then if you pay attention, you see that the same integral just shows up both in the numerator here and in the denominator here. So just gets away. So in the end, this formula is very simple. When you go through a very complicated calculations, and then you end up with a simple result, it means that there must be some short way to get there. And indeed there is. There's a much clever way to but I somehow wanted to follow my own proof, not just because I think that, as I said, it's neither the smartest nor the shortest. But it's another way to looking at it. From my point of view, it's more intuitive. And it's very instructive because it shows you the key point of moving the problem to the electron's moving frame and then getting back. So just putting together, you see, we got the outcoming energy of the upscattered photons in the lab frame is this guy that we calculated here, minus the guy that we calculated here. So if you replace this guy here minus this guy here, is the sigma. You can see that you can also make different considerations. For example, dimensional consideration. You see, you have energy density times area times, well, energy density times c, time velocity. So this is flux, energy flux. Energy flux, time and area is energy per unit time. Makes sense, everything. This is also very useful to make this kind of considerations because you immediately see, you can, from one point of view, it's a so-called sanity check. You make sure that you didn't lose terms. On the other side, it can give you a new way of interpreting that. So it's always very useful, this kind of exercise. So okay, here I just copied the result, and you see, just you can collect sigma Thomson C and new photons, and here you have gamma square minus 1, which is this guy here, plus gamma square beta square over 3. Now we exploit a simple identity, which is very useful also to remember. If you don't remember, it's just a matter of 30 seconds or 20 seconds to prove it. Just gamma square minus 1, you can also write it as gamma square beta square. I invite you to make sure that this is indeed the case. So if you exploit this, you see that you have here gamma square minus 1. So this is just gamma square beta square. So you can gamma square beta square plus gamma square beta square over 3 is just 4/3. And that's indeed 4/3, all the remaining. So sigma Thomson, C, U photons, gamma square beta square. And indeed, that's the result we were aiming at. So we finally proved the total power lost by the electron due to inverse Compton when it travels through a region filled up with a population of isotropic distributed photons. You see that we made no assumption on the spectrum of photons. The only implicit assumption that here I just want to remind you is that the energy of the photons has to be such that the Thomson scattering regime in the moving frame of the electron is fulfilled. So we cannot consider two energetic photons in the initial population. But apart from this very general assumption, we made no, so the spectrum is not relevant. What is relevant here, let's have a look at the most important dependencies, at the most important scalings. Well, gamma square, the first thing to see. And this is something that we should have expected. Sigma Thomson, again, this is the cross-section which gives you the scale. And then you see there is the scaling with the photon's energy density. So no matter about the spectrum of the population of the photon, the more energy you have per unit volume due to the photons, and the correspondingly higher will be the photon, the power lost through inverse Compton by the electron. Now let's work out another quantity, which is the average energy gain felt by the photon. Okay, so the electron loses energy, of course, and the photons, on average, they gain energy, but each photon gains a different amount of energy. Only very few just lose energy, the ones that are chasing the electrons, the very few that are chasing the electron. So let's work out the average energy gain. How can we do that? Well, if you think that's the amount we call just epsilon 1, if you remember with the notation of the last time, epsilon 1 is just the final energy of the photon, so average value. Well, what is this? This is the total energy lost per unit time by the electron over the number of electrons that are, the number of photons that are upscattered per unit time. Just easy. So I should point out that this is not the average, the final average energy of the photons. This is the final average gain, because dE gamma is already a net gain. So what is the average energy gain? That's why I wrote here energy gain. So it's not the average. If you think for a moment, well, you remember that the photons on average, as we will see, increase their energy by a factor of gamma squared. So when gamma is really large, essentially the gain is essentially almost all the energy of the photon. Okay, so when you are speaking about inverse Compton, just changing, considering the energy gain as the total energy of the final photon, you make a very, very small mistake. So we can just, okay. It is as if you are a photon before being a scatterer. If you think of money, someone with money, a photon prior to scattering is just someone with €1. After scattering is one with 1,000 euro. So if you say 1,000 or 1,000 plus 1 doesn't make any difference. It's always 1,000. So that's the point I'm making. So this is something that we already obtained, because the total power in the numerator is exactly what we just come up with. In the denominator, in particular, well, this is just the total energy. This, if you remember, that's the number of electrons that are being upscattered by the photon is just the energy carried in by the photons before being scattered over the average energy. Times, sorry, not over. Not over, sorry, yes. The total energy, so the total number per unit time is the total energy carried by those photons over the average energy. So dN over dt is dE in over dt over average energy. Okay. But again, this guy here we calculated before is just sigma Thomson. This in the denominator is just sigma Thomson C U photons. This is what we obtained in the previous calculation, the previous line. So you end up with 4/3 gamma square, beta square, and then here I call epsilon instead of h nu is the same thing. So the average energy of the photons prior to scattering. And you immediately see that indeed, considering that we are dealing with ultra-relativistic electrons, so if you just take beta 1, which is a very good approximation, in this case, you see that the average energy gain of a photon is 4. So first of all, gamma square. So you see again this factor, gamma square. And the coefficient is just 4/3. So on average, this is the energy gain. So indeed, there is a net gain of energy by the photon, by the population of photons, at the expense of the electron, of course. Now, in the light of this result, so we obtained two results. We obtained, first, the total power lost by the electron due to inverse Compton, and second, the average energy gain felt by the photons. If you combine the two, you can rewrite the total power lost by the electron in a more meaningful way. Why? Look, this is the very same formula here, where I multiplied it and divided by the average energy of the photons before scattering. And this is very meaningful because you see, this, let's have a look first at this term here. This is, again, the average energy gain. So how much energy is gained by a generic photon, on average, of course. Times what? Well, times the so-called collision rate. So how many photons are met by the electron per unit time? Well, this is just the flux from the point of view of the electron, if you think. So sigma Thomson, the speed of what? Of the electron, times the number density of photons. Remember, again, if you have the energy density over the average energy, you have the number density of photons. So number density, so number of photons per unit volume times velocity, again, something density of something times velocity is the flux of the something. So this is the flux of, so number of photons per unit area, per unit time times the cross section. That describes interaction between photons and electrons. And so you have number of photons per unit time. And indeed, this is collision rate. How many photons are being scattered by the electron per unit time? So you see now how beautiful this formula is. You immediately see that you can look at the formula of the Compton power as the collision rate, so the number of photons that are scattered per unit time by the electron, times how much energy on average is transferred to the photons. Very easy, very beautiful, very meaningful. So I would invite you to think carefully. Well, the mathematics here is a little detailed, but you have to think, you have to understand the essence of the line of reasoning, okay? So particularly when you move from one set reference frame to the other, you get back. The assumptions that we made, this formula is very important. And also the way it can be interpreted. If you are in control of all this, essentially you understood everything about, almost everything about inverse Compton. To have a, if you are curious, you see, isn't there any other smarter, shorter proofs? Yes, there are. And in particular, you can find two of them. One, which is very smart, very elegant, in the Rybicki-Lightman textbooks, and another a little more longer, but also nice, in the Longueur. So different proofs. Also to maybe you feel more comfortable with one, or just it's anyway instructive to see how the recent result can be proved in different ways. Okay, so this is a summary of the result we've just come up with. So if I have an isotropic distribution of photons and an electron is traveling through it, it will lose energy according to this power, according to this formula here. Now, if you suppose that not only do you have a photon field, but let's suppose that also the region is filled up with some magnetic field. So you have an ultra-relativistic electron traveling within a region where you have magnetic field, so you know that the Compton scattering is no more the only process through which the electron will lose energy. In the presence of magnetic field, an ultra-relativistic electron is very effective also in losing energy through the emission of synchrotron radiation. So you will have both. And if you remember the analogous formula in the case of the synchrotron radiation, so the power lost, the total power lost by the electron, you remember that you have exactly the very same formula, except for the fact that instead of having here the energy density associated with the photons, you have the energy density associated with the magnetic field, which is b squared over 8 pi in the CG, in the Gaussian system. So you end up that if you work out the ratio between the two source of powers, you immediately see that they scale in the very same way, and they are in particular they are proportional to the corresponding energy density. So whenever this is the case, whenever you have ultra-relativistic electrons that are traveling through a sea of photons, and there is also some magnetic field, if you want to calculate, for example, you want to consider which is the most effective mechanism. I know that the electrons are losing energy through both mechanisms, through both processes. Which one? Is there any one which is dominant? Well, just work out the corresponding energy density ratio, and you immediately see whether there is. So in a region where the energy density associated with the magnetic field is much stronger, it means that it means that most of the electron will lose most of their energy through synchrotron emission rather than inverse Compton. So the ratio of the two energy densities immediately tells you which is the dominant process, if there is any. If they are comparable, of course, the ratio is close to 1. What we didn't see yet, so much in the same way as we did for the synchrotron radiation, if you remember, we first calculated the total power lost by an electron, and so we got this very same formula that we obtained here for the inverse Compton with dependence with gamma square, with energy density, blah blah blah, and then we spent a lot of time in obtaining the radiation spectrum. Remember the role of the relativistic beaming, the critical frequency, all that stuff. In principle, we should go through the very same process here if we want to now derive the spectrum of the radiation produced by the inverse Compton scattering of a single electron moving within an isotropic field of photons. So not only the total power, but the power as a function of frequency. So if you want the specific power, so the spectrum, what I keep calling the spectrum. I'm not going to prove this, but I show you the result, which is this graph here, and I'll make a few comments. So you immediately see that this is the power density. By density, I mean per unit frequency. As a function of what? Well, you see here, given that the final frequency of the photon is a factor of gamma square, the initial frequency, if we call nu zero the initial frequency, you see that, and we know that the average of this value is 4/3, for example. We already know now. You can wonder, so given that the same electron will scatter all the photons to different energies, you have a spectrum. So the result is this function here. you see you have a peak close to the maximum gain. And which is what? If you remember, the maximum gain is 4 times 4 gamma squared. And given that this is nu over gamma squared, nu zero, this is right 4. This is the maximum energy gained by a photon, 4 times gamma squared, the initial frequency. You see? And this is also close to the most probable. So if you could work out the average value of this is kind of probability density function. If you can work out the average value of this function, you will come up with 4/3. So right here, some here, okay, 4/3. And then again, this is something I just commented. So the maximum energy is 4, factor of 4 in this scale here, and this is right here. I'm not going to prove this. This is the mathematical formula which describes this function that you see here. So this is indeed the spectrum. If you want to see a proof of this, this is quite lengthy. It's not worth for this kind of course. But if you want to see that, I advise you the longer to have a look in the longer. Just a few comments. You see, nu zero is the frequency of the initial photon. So let's suppose that, for example, we have not only the population of photon is isotropic, but they also have the same frequency, nu zero. So what's the resulting population of upscattered photons? That's exactly the answer is here, and the formula is here. Let's have a look. Well, n is the specific photon density. So number of photons per unit volume per unit frequency of the initial population of photons. You see, from a dimensional point of view, here you have frequency square time frequency among square bracket. This is all frequency, so frequency times frequency square over this. And then you get velocity time energy density, so flux time area, it's number of photons per unit time. So this is just the resulting spectrum as a function of frequency, yes, where nu is just the final frequency of a generic photon which is being upscattered by the electron, whose Lorentz factor is gamma squared. As I said, this is just for completeness, but I'm not going to prove it. Of course, I'm not asking anyone to remember this. Is of no use but to know, at least in principle, what one should do that. Now we studied, and we also compared in the most general case. So let's suppose you have a region filled up with photons and magnetic field. And within this region, you have ultra-relativistic electrons. Well, in that case, you have both processes at place. You will have both synchrotron radiation and inverse Compton. Well, you immediately see that you can think of the role of the electrons as a double role. Electrons, when they emit synchrotron radiation, they produce photons. But the same photons, when the region is filled up with photons and the optical depth is sufficiently large, each of the photons that are created through synchrotron emission, they have some probability to be upscattered by the same electrons. The same, I mean, not the very same single photon by the very same. Well, here, let's have a look at this figure. Let's suppose here, okay, here you also see the direction of the magnetic field. So is it's coming into the page. So if you think of the Lorentz force, you see, by considering that the electron has a negative charge, you immediately see that magnetic field just deviate, the trajectory of the electrons is this way, okay, because of the magnetic field. So the photons produced by synchrotron emission will be produced by the electrons and will be just this way, produced this way along the beaming radiation, the relativistic beaming of the electron. But then, as I said, if there is the region is depending on the optical depth, on the size of the region itself, not only on the density of the photons and on the number of electrons, the probability, there is some probability that these photons that has been created through synchrotron get inverse Compton upscattered by another electron. And then, again, if the region is particularly large enough to have an optical depth which is large enough to make the probability not so negligible, it can be upscattered twice. But if you remember, at each upscattering, the photon gains a factor of gamma squared. So even just allowing for two upscatterings, two inverse Compton scatterings for the same photon, so the energy of the photon which finally escapes the region can be really large, just as a consequence of these two consecutive upscatterings. So this combination of process is called synchrotron self-Compton, shortened as SSC. The synchrotron self-Compton means that in the same region, photons are created through synchrotron emission, and then the same population which is responsible for their creation can also upscatter them. Particularly when the probability for two scatterings is no more negligible, this becomes a very powerful way to lose energy of the region of the electron, because of the dramatic energy gain that photons undergo at each single scattering. One scattering, gamma times, and then that energy of the photon is again increased by another factor of gamma squared because of the second scattering. So when the photon finally leaves the region, just brings away a significant amount of energy. So this combination can be a really powerful way to cool this region, so to extract energy, okay? So to cool the electrons. And because of this, of the power of this mechanism, there is also a limit, which is called Compton limit. And this is the case in which the energy density associated with the photon field can be comparable with so when this ratio approaches 1. In that case, you have so many photons, so the two processes are working with comparable power. So there is a limit beyond which, let's suppose you want to increase the temperature of the population of the electrons. So you want to give energy, to increase the kinetic energy of the electrons, okay? If you do that, there's no way you can, up to a given limit, there is a limit that I'm about to comment, beyond which you cannot increase the temperature of the population of electrons. Why? Because if you keep on adding energy, kinetic energy to the electrons, all this energy will be dramatically dissipated by the synchrotron self-Compton. Because if you slightly increase the energy, there is a mechanism, in particular with the second order scattering, which you increase the energy. So if you think you increase the gamma of the electrons, so you increase the power of the synchrotron emission with gamma squared. And given that the Compton scattering has a comparable power in this case, you have a huge increase. But you know that particularly when you have two scatterings for a single photon, the amount of energy which is leaving is considerably higher. So it's a mechanism which is such that you cannot go beyond, because you try to make electrons little hotter, and you immediately have a strong dissipation of energy thanks to the multiple inverse Compton scattering. I'm not going to prove this, but it is possible to see that this limit is matched by a corresponding maximum value for the brightness temperature. So in particular, if you consider the source in the optically thick regime, you can associate, you can think of brightness temperature, just imagine you measure the intensity of the field, so you can associate immediately, by definition, the brightness temperature to the radiation coming out of this region. And it's possible to see that there is a strong dependence of this ratio on temperature, so that if you increase the temperature, just if you try to increase the temperature, you would immediately have all the energy dissipated through Compton, inverse Compton. And I just tell you the maximum value of the brightness temperature, which is 10 to 12 Kelvin. So whenever you measure the intensity of a source, it cannot be larger than 10 to 12. Whenever this is the case, there are sources whose brightness temperature is indeed above. It means that something there is something that you didn't consider in this case. We will see that essentially there are two possibilities. In one case, you have to consider the possibility that the entire source is emitting through a coherent process, in which case there is no more limit of this case. Or the second possibility is that the source is moving ultra-relativistic, not the electron, the source. The source is moving towards you with at ultra-relativistic velocity. I'll get back to this. So for the time, for this course, it's enough that you remember that there is a limit which is matched when the two powers become comparable. In that case, you cannot go beyond the corresponding brightness temperature of 10 to 12 Kelvin. Whenever you measure something beyond, it means that there must be an explanation. There is no violation of this limit. So the two possible explanations is that the source is moving relativistically, and I will show you in a moment, or because the process is coherent. And I'll show you an example at the end of this course of a coherent process which gives brightness temperatures of 10 to 35. So orders of magnitude beyond, but there's an explanation, because in that case we are not sure, but almost sure that the explanation in that case is strong coherent emission. So if you remember also what I said about the black body emitter as the most powerful for a given size, a given temperature, is the most efficient radiator, unless you called for a coherent process. So in which case, all the atoms that are responsible for the emission are working coherently. In that case, there is no more such limit. Here it works exactly in the same way. As I said, this was indeed observed in some cases in studying the radio fluxes from AGN, the active galactic nuclei. And in particular, I'll show you in a moment, that's the new slide. The next slide is the new one that I added. I show you that based on the so-called variability of the source. So what is the variability? Well, if you measure the flux of a given source, you see that the flux can change depending on the source. And you immediately see the time scales over which you have a significant change. So for example, it doubles or so it changes by a significant fraction. This time scales is related to the size of the source. So by measuring the time scale associated with the source, with which a source can change its flux, you can have a clue on the size of the source. And I will show you how. I'll show you why. So let's call delta T the so-called variability time scale. So time C, you have kind of upper limit on D, where D is the size of the source responsible for the emission that you're observing. So they saw, in the case of AGN, they saw variability timescales of the order of hours. So even if you don't resolve the source, so you cannot measure the angular size of the source, but you measure the variability, you somehow can measure the size of the source. You measure the flux density, using the variability argument, you measure the size of the source. So if you know the distance, you automatically know the angular size of the source, even if you cannot measure directly. You measure the flux, you measure the angular size, so you can work out the intensity. Once you know the intensity, you can calculate the brightness temperature. They found out that indeed, as I was mentioning before, the brightness temperature was indeed above the Compton limit, 10 to 13, 10 to 14 Kelvin in the case of AGN. But as I was mentioning, we will see sources which are well beyond. So they really understood the solution when they admitted the possibility that the source responsible, the matter which was responsible for the emission, was moving at relativistic speed. Why? Well, first of all, let's consider what happens to I, specific intensity, when you have a relativistically moving source. Well, you know that I, again, something that we already exploited today, is something which scales with delta cube. But delta cube, when essentially the radiation, when you are looking at the source close to when the source is approaching toward you, so the line of sight is close to the direction of the motion of the source, the Lorentz factor is essentially, the Doppler factor is essentially the Lorentz factor, okay? So I scales with gamma cube. But if you remember the definition of brightness temperature, which is just the black body in the case of Rayleigh-Jeans regime, okay? This is just definition of brightness temperature. So you see that when you have a relativistically moving source, so you measure I enhanced by a factor of gamma cube, because that's the intensity that you measure. But given that in the denominator you have nu, also the frequency of the photon is increased by a factor of delta. So delta cube over delta square, there's a factor of delta is left, so a factor of gamma. So it means that if you imagine you have two sources, two identical sources, one which is still or is not moving at relativistic speed, and the other one which is approaching you at relativistic speed. Even if in their commoving frame they have the same intensity, you will measure an intensity of the relativistic source, which is gamma times larger. And that's a piece of the explanation. So beware, people. You measure a high brightness temperature, but that could be the effect of an approaching source at ultra-relativistic speed. So you have a gamma factor, which is just due to relativity. But there is also another aspect, which is number 2 here, which is the variability. When you use the variability to estimate the size of the source, when you are in the presence of an ultra-relativistic source, the relation between the size of the source, d, and the variability timescale, delta t, is no more c delta t. There is a factor of gamma squared. And the proof of this is what I will show you next. So it means that if you think you are dealing with a non-relativistic source, you say, okay, I measure delta t, I estimate d as c delta t. No, you are, if the source is ultra-relativistic, you are underestimating the size of the source by a factor of gamma squared. But if you think, when you calculate the intensity, you measure the flux and you divide by the angular size. But in this case, if you are not aware that you are dealing with an ultra-relativistic source, you are dramatically underestimating the size of the source by a factor of gamma squared. So when you calculate intensity, you calculate flux over angular size. You are dividing by something which is much smaller than what you should really use. And that brings you to an overestimation of the intensity. So these are two independent aspects, both strongly connected with the ultra-relativistic motion. So again, you see why special relativity is so important in astrophysics, because whenever you are dealing with ultra-relativistic sources of radiation, things can change a lot. And here we see two aspects, both the intensity that you measure, and second, the angular size of the source. So both work in the same direction, in the sense that you are led to overestimate the intensity. Once you take into account that, and you correctly estimate these quantities, take into account this relativistic beaming effect connected with relativity, you immediately see that the Compton limit is no more violated. So indeed, this is an explanation. And this can be used as a hint. So whenever you measure and a brightness temperature which is above the Compton limit, it can be a hint, a clue. You should wonder, oh, isn't it that I'm coping with an ultra-relativistic source? And yes, the second option, as I already mentioned repeatedly, is that instead of asking for all ultra-relativistic source, ultra-relativistically moving source, is just because it's the process itself that is no more incoherent, but it's a coherent process. So this is the slide I wanted to add. So how, in general, starting from measuring the so-called variability timescale, is it possible to estimate the size of the source, or to constrain better the size of the source? Let's consider sources which are causally connected. So it means that everything that happens in one single point of the source is causally connected with the other point. Okay. So let's consider the non-relativistic source. Let's consider you are here. You are a generic observer here, right on the right side of this figure. So if you take, let's suppose that some point, I don't know, here there is being something which then affects all the points lying on the surface at the same time. But you see, if something happens, you can think of an explosion, for example, an explosion that took place in the center and then it's expanding in a spherical way. So if you consider two different points, you receive radiation from these two different points. So something is going on at the same time in these two different points. You can think, as I said, as a blast wave expanding through the medium. Of course, you as an observer, you're not going to receive all these photons at the same time, just because of the different light travel paths. In particular, if you take these two extreme cases, you see that there is a delay, which will cause a delay in the arrival times of the photon. So even if the surface of the source is being affected at some point by something which is simultaneous, so the same time is taking place here and here, you don't see just as an instantaneous event. You will see it as a gradual event, because you first see something which is happening here, because these points here have the shortest light travel path, and here the longest one. So in particular, you will see something changing, not instantly, but on a time scale, delta t, which we call delta t mean. There's no way, even if there's something occurring simultaneously, you're not going to see something instantaneous. There will be some time interval. So we call this, and if you just work out, if we call r the radius of the source, just in this case I just took a spherical source, but this is not the point. So you see that the so-called minimum variability time is just r over c. Minimum, because you cannot cancel out the effect due to the extension of the source. The fact that the source is extended, it means that you receive radiation from different points, and these different points have different light travel paths. So the total signal will be smeared out, will be just distributed over a time interval. You cannot avoid this. And you see, the bigger source, the correspondingly bigger the minimum variability time. If, for example, if God could switch off immediately, instantly, the sun, you don't see just all the sun disappearing just at once. You just see the closest point to you, the center, and then as time goes on, just the outer part. So you will see, if you measure the flux of the sun, you will see just not a sudden drop, but something which just smoothly drops. And the time scale is provided by r over c, just like that. So the non-relativistic case is easy to understand. Let's have a look at how relativistic changes things. So we assume that the surface which is responsible for the irradiation is now expanding ultra-relativistically. But now you see that you don't receive radiation from all the points like in the previous case. Because of the relativistic beaming, you will see just a spot here. And the angular side of the spot is again our old friend, 1 over gamma. So the angle here, you just see the corresponding, you receive radiation only from this spot here, whose angle at the center is just 1 over gamma. But now, let's consider the two extreme cases. You receive radiation from this point here, and the other boundary case is here, not here, here. So the difference in the light travel time is this guy here, you see? The small piece, this is the only difference between the two paths, you see? So how can we calculate that? Well, that is, which I just denoted as this gray line here. Well, if you think this is just r, total radius, minus what? Minus the projection of this guy here, minus r the cosine of this angle. This angle is 1 over gamma. So the numerator here is just the path, this very tiny path. Given that you want to calculate a time interval, this is just traveled by light, so over c. But now you see, when gamma is large, it means that you have the cosine of a very small quantity. So you can Taylor expand. So cosine becomes 1 minus 1 over 2 gamma squared. So you immediately see the delta T mean, apart from 2, there is a gamma squared. So it means that, well, this is delta T mean. If you consider a generic delta T, it means that this becomes greater equal in this sense. So it means that in this case, if you compare the two relations, you see that when you are dealing with an ultra-relativistic expanding source and you measure delta T, in reality, you have to multiply by c, but also by gamma squared. So again, if you don't know this, you strongly underestimate the size of the source. Because you say, oh, c delta T gives you the limit. No, it's gamma squared times larger. Because otherwise you think the source is like this. No, the source is much larger. If you will attend my course on multi-wavelength, multi-messenger astrophysics, there is something which is my main subject of research, which is gamma ray bursts. Gamma ray bursts are just ultra-relativistic jets of matter expanding with Lorentz factor up to 1,000. So if you don't take into account this is total disaster. These effects are dramatic in that case. Okay, so I think that I can stop here because we already... So on Wednesday, we will see again the beautiful lab of the Crab Nebula that we already seen when we talked about the Compton, the synchrotron radiation. We will see that in the very same spectrum of the Crab Nebula, we also see at play the inverse Compton. So the same electrons which are responsible for synchrotron emission of many different energies are also responsible for upscattering low energy photons up to very high energy photons. Self-synchrotron, Compton. Synchrotron self-Compton. So we will see the detail of this, okay? So unless you have questions, I'll stop here. Okay, yes. Okay.